See if we have any more of these. Ooh, we got something different. So now we're trying to find the volume of something that's bounded by the lines y equals x minus 4, 4 minus x, and we're going to do it with a couple of things here. Sorry for not having this organized, but here we go. So first let's plot this and see which one's top, which one's bottom, how we set it up, and all those kind of details. So start out with an x and y axis. I actually can pop up a grid here for us. Put it on top. Okay, so if we have an x and y axis, here we go. Put it right here in the middle. Here's my x-axis, or my y-axis, here's my x-axis. And I got two lines. I'll draw these in gray just so they stand out a little bit. We have x minus 4, so that's 1, 2, 3, 4 down here. So we have a line that looks kind of like that. And we have another line which is 4 minus x. That's going to look like this. And then we're also bounded by the line x equals 0, which is really just this axis. Go ahead and take that one back because we know we already have an axis there. So now I'm looking at this region. Let's go ahead and color it in a little bit. Looking at that region. My base, again, is just that cross section from the top to the bottom. This is my base. So I need to figure out what that is. And my base is going to be top minus bottom. We'll call this the top. That's 4 minus x. And the bottom is equal to x minus 4. So the base is the top minus the bottom, which is 4 minus x minus x minus 4. And if we were to simplify this and combine a few things here, this negative distributes, so I'm going to have 8 minus 2x because I got two negative x's and this negative 4 makes a positive. So there's my base, 8 minus 2x. Then what I'm going to be looking at is my shape. I need to make squares, and the area of a square is just base squared. And we're going from A to B. So where do we start? Where do we finish? We start here on the axis at 0 and we finish at x equals 4. So we're going from 0 to 4 of the base squared dx. There's no constant because it's just a squared. It's just a square. So then we're doing the integral from 0 to 4 of 8 minus 2x quantity squared dx. I know that we can evaluate that, but I'm worried mostly about setting it up just like we've been doing with this whole workbook, just for time's sake. Equilateral triangles. Again, a quick reminder. It looks like this. And we've also been noticing that we have a height here down the middle, and that height winds up being b over 2 because we say this is b over 2, this is b over 2 because the whole thing is b. The whole thing is our base. But then we make two right triangles, so this one's going to be b over 2 as well. Then the area of that, oh, wait a second. This is equilateral triangles. I was thinking right isosceles triangles. Let's stretch that out a little bit. Make it more equilateral. So we know that these are still b over 2 because the whole base is just b. But because it's equilateral in a 30, 60, 90 triangle, that changes the relationship. So this is b over 2 times the square root of 3. So the area of an equilateral triangle in terms of the base is 1/2 the base times the height, which is 1/2 b times the h is b over 2 times square root of 3. So when we simplified that, we got square root of 3 over 4 times b squared. So we're going to set it up exactly the same as before, except now we have a constant outside. So the volume for this one is equal to the integral from 0 to 4 but we got a square root of 3 over 4 on the outside, and we still have 8 minus 2x, our base, squared on the inside, dx. Now that we kind of know what the base is, we don't have to keep redrawing it, but let's take a look at a couple of more shapes. We got semicircles and isosceles right triangles here. So for a semicircle, alright, sorry about that hiccup. Just had to pause it for a second. You probably didn't even notice. But anyways, we're looking at these last two shapes, semicircles and isosceles right triangles. So first, semicircles, if we're looking at a semicircle where this is the base then represents the diameter. But there of a semicircle is 1/2 pi r squared. It's half because it's semi, it's only half of it. But in this case, r is equal to the base over 2, so it's going to be b over 2 quantity squared. Ooh, it looks like I missed something before, because this constant needs to be b over 2 squared times a half. That's going to be pi over 8. So I missed that on one of the earlier problems, pi over 8b squared. Similarly, we got the isosceles right triangles for that shape. We have a shape kind of looking like this, and this is one that I started to do, but it was getting a little bit incorrect. We know that the whole thing is the base. That means each of these halves is b over 2, or the base divided by 2. That means the height is also b over 2. Why? Because this creates another pair of isosceles right triangles up here, where these are each 45 degrees, and that's 45 degrees, and 45 degrees, and 45 degrees. A lot of symmetry going on here. So let's set up these pieces. We know that our top and bottom, top minus bottom comes out to be 8 minus 2x. That's our base, and we're always having our base squared. We're going from 0 to 4. The difference now is looking at the constant. For this one, it's going to be pi over 8. For the next one, it's still from 0 to 4. It's still 8 minus 2x quantity squared. Both of these are dx, by the way. But now the constant is, if we have the area of one of these triangles, it's half the base times the height. Well, half the base is 1/2 b, or b over 2, but then the height is also b over 2. So that's going to be 1/4 b squared. So this is just 1/4. Whoops, 1/4 on the outside. Easy, breezy, lemon squeezy.